Alright, we're going to solve for you a oblique launch or a non-horizontal launch projectile motion problem. Here we have, it says it's a cannonball shot from a cannon at 60-degree angle. We're going to assume that's above the horizontal. Cannonball leaves the muzzle with a velocity of 200 meters per second. We're going to determine a lot of things here, including horizontal velocity, vertical velocity, accelerations, how long it's in the air, that's our time, maximum height, and the horizontal displacement, our delta x, or our dx. If we go over here, I've already kind of drawn a picture out for us. Here we have our velocity, our muzzle velocity. That's going to be our initial, our actual velocity that it leaves the cannon with. It's going to take an arc here. This is a parabolic arc, and it's going to hit the ground at some sort of distance away. First thing we're going to do is we're going to set up our right triangle here. We have Vx, Vy, 0. If we blow this triangle up, just so we can see what exactly we're doing here, we have 60 and we have 200 here. And this is our right triangle. If you remember back to geometry, you know how to solve these triangles using trig. If this is our angle here, then this is going to be our opposite. So if this is opposite, this is hypotenuse, we're going to use the sine of theta equals opposite over hypotenuse. Well, plugging in what we have here, it's the sine of 60 equals opposite over 200. So we do 200 times the sine of 60, okay? You might want to do that in your calculator first. Sine of 60, cross multiply times 200, and we'll get our opposite is equal to 173.2 meters per second. And since that's what this velocity was here, we're going to continue with those units and be meters per second. All right, this is equal to our Vy0, okay, or our initial vertical velocity. Here we have Vx. Remember back to trig, this is our adjacent side, so we're going to use the cosine of theta equals adjacent over hypotenuse. Well, we have 60. Our hypotenuse is 200. So 200 times the cosine of 60, we're going to cross multiply. We'll get our adjacent, and our Vx works out to a nice even 100 meters per second. Okay, great. Vx, and this is our Vy0, or our initial vertical velocity. I'm going to erase all this and we'll go back over here. So 173.2, 100, and of course meters per second, meters per second. All right, so we have solved our first two things here. A and B, initial horizontal velocity, initial vertical velocity. Both of those are Vx and our Vy0. Our horizontal acceleration. So let's think about what's happening to the cannonball as it flies through the air. As it flies through the air, as this cannonball takes off and it goes through the air, it is not going to accelerate horizontally. Okay? If it goes up in the air, the only thing that's affecting it, in the absence of air resistance in a perfect world here, right? In the absence of air resistance, the only thing that's affecting it is the force of gravity. So as it goes up, it's going to be pulled down by gravity, but gravity doesn't affect it moving horizontally. So our horizontal acceleration then is 0. It's just going to keep traveling forever. We know this because if we went to space, there's no gravity in space, and we take a baseball and we throw a baseball in space, it's going to go forever. It's going to go in a straight line, right, forever. It's not going to change. But on Earth, we know if you throw a baseball, it's going to go up and it's going to come back down, and that's because of gravity. So our horizontal acceleration is 0, and our vertical acceleration is 9.8 meters per second squared going down. So sometimes we call that negative 9.8 meters per second as it's squared as it's going down. Okay, horizontal acceleration, vertical acceleration. This is important as we solve this problem, knowing our vertical acceleration. All right, how long it will remain in the air in seconds. Okay, we're looking for time. Okay, go back over here. If we're trying to find time, we need to know then what our height that we get up to here, and we need to know how far it's going to go, and we need to know how long it's in the air. The easiest way to solve for this problem is if we already know what this Vy0 is, right? If we go back to our equations, we know that, use a different color here, Vy equals Vy0 plus AT. Now some of y'all may have a little bit different equations, but they're the same equations. They're essentially the same things. Vy equals Vy0 plus AT. So, a couple different ways to solve this same idea. Okay, you're going to get the same time. When this thing goes up, it's going to have an initial vertical velocity of 173.2 meters per second. When it hits the ground over here, it's going to hit the ground with the same vertical velocity, just going the other direction. It'll look something like this over here. Our triangle, if our triangle is like this here, where this is our vertical velocity going, or this is our actual velocity going up, we flip it up like this and it's going to go down. Notice how this and this haven't changed. It's just going up, it goes up, and then it comes down and it hits down like this. So, as it goes up, it's going to come down here. So our vertical velocity is now going this direction, so it's going to be negative 173.2 meters per second. This here is not changing, right? Vx never changes. That's still 100 meters per second. So this is our actual velocity, which essentially would be 200 meters per second. So Vy0 plus AT. Vy, meaning this is our velocity over here, that's going to be negative 173.2 meters per second equals 173.2 meters per second plus our acceleration is, of course, if we're on Earth, doesn't say it, we're going to assume it, 9.8 meters per second squared in the negative direction. And then this is what we're looking for, our time. How long is it in the air? Okay, we subtract over here, we get negative 346.4 meters per second equals negative 9.8 t. That's 35.35 seconds. Okay, so just go. Okay, so after we do our division here, we're going to get 35.35. Let's make that an S seconds. Okay, 35.35 seconds. That's the amount of time in the air for the cannonball. Great. That tells us a lot of things. 35.35 seconds. I'm going to write that over here so I don't forget it. Equals 35.35 seconds. Make sure you write that on your paper as you're working this here. All right. Going back to our problem here, we need to know the maximum height reached. We want to know how high in the air does this get. We call this delta y dy. Okay, it's the same thing. It's this y. Okay, I'm going to call it delta y dy. It's our distance up in the air that it's going to go. If this is 0, how high does it go? All right, well, how long in the air, how long does it take for that object, that cannonball, to get to that distance? This thing is completely symmetrical. Believe me, trust me, it is. It's symmetrical. So if it takes 35.35 seconds to get from here all the way to here, guess how long it's going to take to get from here to here? This divided by 2. So our t1/2, or our time for half of the trip, is 17.7 seconds. 17.7 seconds to get to here. Why this matters? Because we're going to find the maximum height reached. Right? We're going to calculate this here. We have a formula for this. Delta y, okay, or dy, equals Vy0t plus 1/2 AT squared. All right, here's our formula. If we look here, and we're going to do delta y, and that's what we're going to solve for. Does it matter if we find from here up to the top, or if we find from the top down to the bottom? It doesn't matter, right? This is the same distance either way. To make it easier on ourselves, why don't we just solve from the top? We'll pretend we're halfway through the trip, halfway down here. Okay, delta y equals, if that's the case, and we know that this is the top of the arc here, then this Vy0 here, this initial vertical velocity up at the top, 0. Right? It's not going up anymore, it's not going down anymore, so that is 0. So that's 0 times our time, doesn't matter, right? 0. Plus 1/2, okay, negative 9.8 meters per second squared, times our time.
Now we're recording. Go back to where you started with the second line there.
Right. So when we work all this out, we get delta y equals 0. This is because this is 0, plus 1/2 negative 9.8, 17.7 squared, we're going to get that that distance up in the air is 1531. The most common mistake here is using our full time, our 35.35 seconds. If we use that for our time, we're not going to get the right distance. So we need to use our half time because we're only finding this distance up in the air. Okay? That's our maximum height, 1531 meters. All right, last question. The horizontal displacement, that's the range. How far does this cannonball, when we shoot it, go in the air? Okay. I should say, not how far does it go in the air, how far does it go along the ground? This is the easiest one, right? We know that delta x equals vxt. It's our simple velocity equals distance over time. We rearranged for distance, so delta x equals, what's our Vx? Never changes, right? 100. Now, do we need to use our full time or our half time? Well, if I wanted to know how long it would be to get halfway there, then I would use half of my time, but I don't. I want to know the whole trip. 100 times 35.35, which we found earlier. Okay, seconds, meters per second, we'll make sure I have our units. Delta x equals 3,535 meters. No problems, right?
This has been a Muddy Burrow production.